10.4, alternating series. So this section will introduce us to alternating series that contain both positive and negative terms. So you're going to be learning the alternating series test. This will only apply when you have a series that is going plus, minus, plus, minus, plus, minus. So, you know, you're probably going to see -1 to the n somehow in there. Or, you know, it might have it be like, oh, I don't know, negative n, you know, over something, you know, but you could pull the -1 to the n out, okay? So, you know, it doesn't always have to, you know, be there like that, but a lot of times you will see it specifically like that, and you'll know it's an alternating series, so you want to apply that alternating series test before you think about anything else. So let's explore it with the harmonic series. So given the harmonic series, consider the idea that you wanted to have the signs alternate on each term. What would you need to do to the formula to cause this to happen? And so just what I just said, we would put a -1 to the n on there. And then if my n is 1, I'm going to have, you know, let's say I wanted it to start with a positive. So you might have to make this -1 to the n minus 1, right? Because if you put a 1 in, then this would be -1 to the 0 power. Okay, so start positive, or I'm going to put this one up here, -1 to the n over 1 over, or times 1 over n. This would be start negative. Okay, so so here we go. If we did our partial sums, the sum of the first one. So if I put 1 in, I would get +1 over positive, -1 to the 0 is +1 times 1 over 1. I would get 1. If I did the second partial sum, that would be the first term plus, and then I would do a 2. Well, that would give me a -1/2. Oops, I'm doing 2. Sorry. Then if I did partial sum of the first 3, the third one would give me -1 to the 3 minus 1, was -1 to the second, which would be +1 times 1/3. So that would give me 1/3. So if I, you know, I could keep going. You could see what's happening. This next one would be -1/4, okay? So you can see that your alternating series changes. So like I said, if we are going to start positive, that means that our first, the partial sum for the first was greater than 0. And if I want to start negative, that would mean that my partial one for the first would be less than 0. So for this one up here that I did, I'm just going to do it in a different color. Your first term would have been -1. Your second term, or your second partial sum, would have been -1 plus 1/2. Your third partial sum would have been -1 plus 1/2 minus 1/3. So you can see what I mean by having your first partial sum be less than 0, so it's starting negative, or having your first partial sum be greater than 0, meaning it's starting positive, okay? So if you were going to model this using a number line, let's put 0, 1 here, and our first partial sum is 1, so we would have it's 1 minus 1/2, so, you know, we're doing 1 minus 1/2, so we end up at 1/2 here. And then our third partial sum, we would be adding 1/3. So that puts us, I think, about 5, 6. And then our fourth partial sum, we would be subtracting 1/4, and I think that puts us at 7/12 or something like that, which is just a little bit bigger than 6/12, which would be 1/2. So you can see how the sums oscillate back and forth. And so you can kind of see that it, you know, that it, for this one, you know, we know that, that our harmonic series on its own does not converge, okay? But look at this. So by definition, an alternating series is a series whose terms are alternately positive and negative. Alternating series can occur in two ways. Either the odd terms are negative or the even terms are negative. And so the alternating series summation n equals 1 to infinity of -1 to the n times a sub n, and the summation from n equals 1 to infinity of -1 to the n plus 1 times a sub n converge if the following conditions are met. If every a sub n is positive, well, that means don't count your plus minus, okay? Don't count that -1 to the n. Are all those other series all positive? Does the limit as n approaches infinity of a sub n equal 0? And the third thing is the second, or like, you know, like the term right after a sub n, is it going to be always less than the one right before it? Okay, that's what number 3 says, that, you know, basically it's decreasing, right? This one says that it's decreasing. So, you know, does the limit as n goes to infinity of a sub n equals 0, is every single one positive without the positives and negatives, and is it decreasing? So, verbally speaking, a series converges if its terms alternate in sign, decrease in magnitude, and have a limit of 0. And so, word of caution, this does not say that if the limit as n goes to infinity of a sub n does not equal 0, the series diverges by the alternating series test. The alternating series test can only be used to prove convergence. It does not say that if the limit as n goes to infinity of a sub n does not equal 0, then the series diverges by the nth term test for divergence, not by the alternating series test. So if it doesn't equal 0, if this limit as n goes to infinity of a sub n does not equal 0, then it's going to diverge by the nth term test, which is the very first thing that you should always check. So always check this first. Always check first to see if that limit goes to infinity. I'm sorry, if the limit as n goes to infinity is 0 or not. If it's not 0, then you can say right away that it diverges by the nth term test. So, what do you think about our alternating harmonic? What do you think about the alternating harmonic? Does the alternating harmonic series converge? Because I know the regular harmonic series does not converge. But does the alternating harmonic series converge? Okay? You need to think about that because, and we'll talk about that near the end. But, you know, think about it. Think about, you know, all the things that need to be true. And if all these things are true and it's alternating, I'm pretty sure you're going to see that that alternating harmonic series actually converges. But the one that's not alternating, just the regular summation of 1 over n, does not. Okay, so let's look at example number 1. determine whether the following series converge or diverge. I notice that it is alternating, okay? So I'm going to go ahead and look at my a sub n, and this is without the alternating piece, okay? Because we are looking for three things, and it all involves, right? It all involves just the regular a sub n. So to do that, let's just look at, if I made it 1, so my a sub n is 1 over n squared without it, okay? So if I was showing you what they were, when n is 1, that would be 1, plus. When n is 2, it'd be 1/4. When n is 3, it would be, and really, I shouldn't be putting plus because I'm not really listing the series. I'm listing the sequence. 1, 1/4, 1/9, 1/16. Because we just want to look at this and we want to say, okay, well, first for my a sub n, are they all positive? So number 1, yep, they are all positive. If I looked at the limit as n approached infinity of 1 over n squared, do I get 0? Yes. And then are all my, is the fourth term smaller than the third term? Is the third term smaller than the second term? And it looks like they all are, okay? So all of these things are true for just my a sub n. So therefore, this is going to converge. So I'm going to say, number 1, my a sub n is greater than 0 for all n. Number 2, my a sub n plus 1 is less than or equal to my a sub n as n goes to infinity. Number 3, the limit as n goes to infinity of 1 over n squared is equal to 0. So therefore, summation n equals 1 to infinity of negative 1 to the n over n squared converges by the alternating series test. Okay, so let's look at B. Okay, we notice we have an alternating series test. I know that my a sub n is going to be n squared over n cubed plus 1. I'm going to just look at what my values would be if my n is, and it starts at 2 here. So if my n is 2, it would be 4/9. If my n is 3, it would be 9/28. If my n is 4, it would be 16/65. If my n is 5, it would be 25/126. ... Okay? So are my values, are my values getting smaller, smaller, smaller? Yes. Okay, they're all positive, and they're getting smaller. So number 1, my a sub n is always greater than 0. Number 2, they are all getting smaller. So my a sub n plus 1 is less than or equal to, and I think it specifically said less than, but I think in my calculus book it uses the term less than or equal to, but I'm going to check that. As n goes to infinity. Number 3, is the limit as n approaches infinity of n squared over n cubed plus 1? Well, I would say that this is the limit as n goes to infinity. I can just look at n squared over n cubed, which the n squareds cancel, and I'm left with 1 over n, and yes, that does equal 0. If I put infinity in that denominator, 1 divided by infinity does give me 0. So therefore, my summation, n equals 2 to infinity of negative 1 to the n plus 1 times n squared over n cubed plus 1, converges by the alternating series test. Okay? All right, let's look at C. So I'm going to change colors. My a sub n is just n over 2 to the n. And so if I was looking at what my a sub n was, if I put in a 1, I get 1/2. Put in a 2, I get 2/4, which is also 1/2. Put in a 3, I get 3/8. Put in a 4, I get 4/16. So, which is 1/4, right? So you just want to make sure that these are, and see right here, you have to have the equal to on there, even though up here, she did not have the equal to on there. So, but technically, yeah, you need that equal to, because look, those can be 1/2. All right, so we looked at, are they all going to be greater than 0? Yes. Number 2, is the second one always less than or equal to the one previous to it as n goes to infinity? And it looks like yes, okay? And number 3 is the limit as n goes to infinity of n over 2 to the n equal to, well, this is hierarchy of functions, because 2 to the n is so enormous that it is going to get very, very large a lot faster than n will. So this actually does go to 0 by hierarchy of functions. And so therefore, it converges by the alternating series test. And then D. So your a sub n is equal to ln of n over n. So let's go ahead and list our values and see what we get. If